So, all right. Now we've officially been warned that we're being recorded. So that's one of the pieces I needed to cover. So good noon to everyone. I'm Jay Solomon with the University of Illinois Extension, Energy and Environmental Stewardship Educator. I'm based in the northwest corner of the state. Glad to have a chance to welcome you to today's webinar. It's U of I Extension webinar co-hosted by the Illinois Geothermal Coalition, which is a group we'll give you a little bit more information about momentarily. And I want to go through a few housekeeping things just to give everybody a heads up. This is being recorded as we were just sharing. Please keep your microphones muted, and you may want to keep your cameras off. That's pretty optional, but it does save on the bandwidth. And I think you'll notice that most of us presenters and associated will turn our cameras off if we're not the ones doing the presentation, just to save bandwidth for everyone. If you have any problems connecting in connection or with audio, let us know by typing in the chat box. And we've shared some things in there. Hopefully you see the chat box being spot down there. If you have questions, keep this in mind as we go through the presentation. Please type them into the chat space. There's a couple of us, Nancy and I'll be keeping an eye, and Andrew will be keeping an eye on that chat, putting those questions together to bring them to the presenters. If we run across one that needs to be clarified as the presenters are going, we'll try to interrupt the presenter and let them know. We'll also try and get this, providing you with the slides after this and links to the resources, and along with once this recording has been posted, let you know where that's being posted at. So a little bit about today's webinar. We're the title, Geothermal Energy in Illinois. We're really focusing on what we can do in this area. This is part of an outreach program we've gotten started. It's actually a geothermal outreach project that several of us are involved in as a grant collaboration. And the effort there is to improve access to the resources that are on campus. And what we hope to do is highlight some of those resources today. A little bit about the background of this. Extension has been involved with energy efficiency and renewable energy, especially my team, the Energy and Environmental Stewardship team, and Nancy's team, the Community and Economic Development team. And we actually have a collaborative grant that we've been doing some work with over the last few years, along with having done consumer and policymaker education in this area of renewable energy, energy efficiency for a number of years. As I say, for the last 4 years, actually 5 years at this point, we've had an Illinois Science and Energy Innovation Foundation, Smart Grid and Energy Efficiency Grant that's kind of led us through some of this stuff. And this is kind of a side project that got started as part of that effort. And then at this point, I want to turn it over to my colleague in this on the Geothermal Outreach Grant to talk a little bit about the coalition. So Andy, I'll turn it over to you.
Thanks, Jay. And good afternoon, everybody. Thanks for joining us. Just wanted to give you a brief overview of the Illinois Geothermal Coalition. It was founded in nearly 2 years ago by myself, Yu-Feng, who will speak today, and Morgan White, who will be a panelist on the August 10th webinar. So basically, we started this coalition after doing some research projects on U of I campus, and both for research and for installing geothermal energy systems. And after we also held an international workshop on the impacts of flowing groundwater on geothermal energy systems. So the coalition is a group of corporations, nonprofits, geothermal professionals, and researchers seeking to establish Illinois as a leader in geothermal energy by sharing experiences with new technology and implementation of existing and future technologies. So we're really supporting the geothermal efforts by all our members, and this will strengthen and advance the implementation and design of geothermal energy systems in Illinois and in the broader US Midwest region. So the coalition is acts as a central networking hub that is a catalyst for advancing wider adoption of these technologies through programs of education, outreach, and engagement. And this webinar series is one of these educational endeavors. So please, if you want more information on the coalition, I'll put the URL in the chat. And if you need want any more questions or have me answer any more questions, or you have any other comments, you can email me and I'll put my email in the chat as well. So thanks, and thanks, Jay. And then I'll send it back to Jay, introduce the speakers. Thanks.
Thank you, Andrew. Appreciate that. And you can see I'm working from notes on this and the slides here. So today's webinar, we're actually going to have 3 presenters in here sharing a good taste of our background and what Andrew just alluded to, the depth of everything we've got going on in Illinois. Our first presenter will be Dr. Tugce, and she's an assistant professor in the Department of Civil Engineering at U of I in Champaign, and specializes in geotechnical engineering. She received a PhD degree, received her PhD degree in geotechnical engineering from the University of California, San Diego. She'll be our leadoff presenter in talking about kind of an overview of geothermal energy and what our opportunities are, and set the stage for the other 2. And you'll notice that there's a pretty tight interweave between the 3 presentations today. So there may be a little duplication, but that has to do with all of us working together. So with that, I will stop sharing my piece of it and turn it over to Dr. Baser.
Thank you so much for the introduction. Hello, good afternoon, everyone. I hope you're enjoying this cloudy, rainy weather. Well, I am. So I'm happy to be a part of this project, extension project, and I'm happy to be a part of this geothermal coalition in Illinois. I believe that since I joined the department at U of I in 2018, we've come so far, and then I believe that our efforts, my colleagues' efforts together will lead to more advanced and state-of-the-art geothermal energy and system development in Illinois. So today's presentation will give you an overview about what is geothermal energy and what are those systems and why do we exactly need it. And then we're going to talk about different types of geothermal systems and their working principles very briefly. And then we're going to talk about geothermal potential of our country. And I'm going to introduce some examples of ongoing projects at the U of I Urbana-Champaign campus. And we will wrap up with the conclusions, recommendation, summary, and I'll be happy to answer your questions at the end of the 3 presentation, I'm assuming. So why energy? I mean, so it's a obvious question because it's all about energy. So the global energy demand is rising, and we all know that the carbon emissions, methane emissions are increasing, and this is how different countries are contributing to this carbon emissions worldwide. And the other driving factor for us to care about energy is the electricity. Electricity generation is the largest source of greenhouse gas emissions in our country. If you take a closer look at this figure here, residential and commercial buildings are responsible for the 32% of the electricity usage in the country. So this was taken from U.S. Environmental Protection Agency. This was reported in 2018. This number has increased since then. In the updated report, it's about 40%. So because today topic of interest is geothermal energy, let's take a quick look. What is geothermal energy? So geothermal energy is the heat derived within the subsurface of the earth. The energy comes from magma because of the radioactive series of radioactive procedures. It radiates heat, and then this heat reaches to the outer crust of the earth at some point. So then this geothermal energy can be directly used for space heating, domestic hot water applications, and also electricity production. So our motivation here is that we could use this energy in the subsurface for multiple purposes that I just explained, but how we are going to do that and why we can do that. If you look at the subsurface temperature contour map of our country, you will see that the subsurface temperature is relatively constant compared to the air temperatures. So especially in regions in Midwest where we experience very cold winter and hot summers. So the ambient air temperature fluctuates a lot. But in contrast, the subsurface temperature after a couple of feet, or maybe 10, maybe 20, this is taken from, for example, from Atlanta. So you see that the annual mean temperature of the subsurface is around 63 Fahrenheit, and it fluctuates very near the surface. But after, for Illinois, after 10 to 15 feet later, so we see that constant temperature about 52 degrees Fahrenheit. So we can take advantage of this constant heat throughout the year to establish our geothermal systems. So geothermal energy is not usually visible, except that we are talking about geothermal energy power plants, especially that exist on the West Coast and the southern states. But it's usually in the subsurface. So we install our subsurface infrastructure so that nothing is visible, but we do have some hardware and plant system that we install in the surface as well. And so there are, depending on the purpose of the usage, let's put it that way. So there are different types of geothermal systems. So I really like this figure because it kind of combines everything that we are going to cover today. So I like to subgroup the geothermal systems in two groups. So one would be low temperature systems up to somewhere here from right to the left. And then high temperature systems from hydrothermal doublet or hot dry rack or enhanced geothermal systems here. So the difference between these two systems are the low temperature systems are usually, not always though, we usually use them for space heating and cooling or other agricultural solutions. And for the high temperature geothermal systems, we produce electricity from them. So if we divide them into the groups, there's a term, maybe you're already familiar with this, maybe you're not. I mean, if you are, this is great. If you're not, don't worry about it. So I'm going to introduce everything in detail. So there are ground source heat pumps, which encompasses shallow geothermal systems, which I like to call them here, 1, 2, 3, 4, 1, 2, 3, and deep direct use applications. And then there are though, so although we are taking advantage of this constant heat budget of the subsurface, we sometimes actually generate our own geothermal system, geothermal reservoir in the subsurface. It's either deep or shallow. And these are called underground heat storage systems. So they can be through boreholes installed in the subsurface, or we can use aquifers, or we can use some cavities in the subsurface to utilize them. So there are, of course, hydrothermal, which are formed naturally, and it includes a lot of water. So geothermal systems are closely associated with water. If there is no water, then we engineer the hot dry rock to put water in it and to generate hot water in the case of enhanced geothermal systems. So let's take a look at ground source heat pumps. So the most common application in the US is the closed loop systems. We first started with the open loop systems because they were easier to install. But because of the groundwater usage restrictions by the EPA in the US, we are not, to my knowledge, we are not allowed to install an open loop system. And there are different versions. So this can be horizontal. So this includes digging trenches in the horizontal direction and then putting heat exchanger pipes, installing heat exchanger pipes that are made by high density polyethylene tubes usually. And so there are some vertical systems where we put this heat exchanger tubing in the boreholes that we drill, or sometimes we utilize ponds or lakes because of their higher heat retention capacity. So these are all through either trenches, boreholes, or we utilize ponds there. So maybe you've seen already the utilization of the pond. Maybe you already have the system in your house because I know that Illinois has some single family houses or community scale geothermal ground source heat pump features here. So another type of this geothermal system is called energy piles or energy foundations. How they work, as you can see this in this figure. So the buildings usually have the foundation elements, which are structural elements that are made with a steel cage that are placed in the shaft that we drill, and then we pour the concrete after that. And by simply putting these heat exchanger tubes, attaching them to the reinforcing cages, we can convert our foundations to become energy foundations. What they're going to do. So this is again will be a closed loop system, which will be these pipes will be directed to the mechanical room in the building, where it will be connected to a manifold, a heat pump, water and water coupled heat pump, or water air coupled heat pump, depending on the type that you choose, to provide heating and cooling to the buildings. So we mentioned there are different heat storage systems. I mean, heat storage systems is one of the options. So early years, like maybe 100, 150 years ago, the tank thermal energy storage system first emerged. This is how we started utilizing the subsurface because we wanted to insulate these tanks and then protect our heat in the subsurface to take advantage of the constant heat of the subsurface again. So there are pit thermal energy storage systems, borehole thermal energy storage system, and aquifer. In the case of aquifer, we usually use a open loop system at this point. So this is where we pump the water up and then use it in the building or in the community and then pump it back to the aquifer. But again, there are a lot of restrictions with the aquifer thermal energy storage system because we do not want to contaminate our groundwater resources. So there are a lot of permits and that we need to obtain before we do this. And yeah, so let's take a look at the geothermal potential of our country. So this figure was published by the Department of Energy in 2017. So this is a temperature scale. Actually, it explains very well how the heat can be used for multiple purposes, using the geothermal energy principles. So as you can see, the low temperatures are generally used for space heating and cooling, building heating and cooling, greenhousing, food processing. So there is the cut at around, it's usually 150 degrees Fahrenheit. After that, so we can use this heat for electricity production through either binary geothermal power plants or flash dry steam or enhanced geothermal power plants. So by just like looking at this map, so you can see that in Illinois, the temperatures are very suitable for geothermal heat pumps. So, but this doesn't really mean that we can only have geothermal heat pumps. There are other solutions that I'm going to talk about in a minute. So there are factors affecting, as geothermal engineers, I would like to call ourselves. So we design these systems based on especially subsurface properties, and these include soil or rock, or I'm going to call them geomaterial type, Their thermal properties are important and their hydraulic properties are important. Hydraulic properties include hydraulic conductivity and hydraulic gradients if there's any groundwater flow, significant groundwater flow detected in the area that you would like to install your geothermal systems. So I'm not going to go into detail how they're affecting the design, but I'm happy to answer any questions that you may have either at the end of the presentation or later on. You can send me an email and I'm happy to answer. So as per hydraulic properties, which is very important for us. So for example, if we are having a higher hydraulic conductivity subsurface, so this provides us a better efficiency for ground source heat pumps, but not really for the heat store systems, because in the case of heat store systems, we would like to retain the heat within a specified volume when we do not really want the heat loss. And for higher hydraulic gradients, when there are groundwater flow, this is again a better efficiency for ground source heat pumps, but not really good for heat storage systems. So there are many projects, geothermal projects going on campus. And the first one that I would like to talk about, my colleague on the call and I are collaborating, have been collaborating. It's a geothermal system installation for campus instructional facility, which is a new building on campus. If you ever been to the campus, this is a Springfield and I would like to say 4th, if I'm not wrong. So now we have a new building that is mainly used for classrooms, for education. What we did here, we drilled a borehole, a test borehole, and it was about 400 feet. And we collected some geomaterial core samples and we brought them into the lab. And then we determined the thermal physical properties of the geomaterials, and we monitored the ground temperatures and also thermal hydraulic properties, which I just mentioned that are really important for the design. And so this system consists of 40 boreholes. The initial plan was 60. And after our investigations, we reduced the number to 40, which actually saved us some money. With a 300 feet deep vertical heat exchanger loops, they were installed in a loop. And then, so this system is expected to provide heating and cooling to the building and reduce the building energy consumption by 65%, which is a very significant number. And this is the state of the art that you're seeing here. It's our major contribution to our campus. Another project my colleagues and I are collaborating is the energy piles, energy foundations for the new hydro system laboratory building, which is a new addition to the actual replacement to the civil and environmental engineering building. So this was the plan of the foundations. You see 1, 2, 3, 4, 5, 6, 7, 8 foundations, and we decided to utilize 4 of them. And so this new building is connected to the existing Newmark civil engineering building with a very nice smart it's called smart instrumented bridge. And here are the locations of the foundations. And what we did here, as I mentioned earlier, we simply converted them to be energy foundations. So we put heat exchanger loops, we attached them into this, the rebars to the cage. And then we lowered them in the drill shafts and we instrumented them with temperature fiber optic cables, temperature sensors, and also strains to investigate the long-term effects. And so now this is all installed and the system is not yet operational, but so this is a both research project and it is contributing to the heating and cooling of the geotechnical engineering laboratory in this new building. So another project, it's for the greenhouse at the research park on campus. So the way that it works, you're planning this greenhouse, and then the way to do it to install this horizontal loops, and then just connect them to a heat pump again. So the heat can come from different resources. So if this is coming from, for example, another renewable energy resource, which is great. So this system is proven to reduce the energy consumption, energy cost by 60% when it's compared to the traditional HVAC system. The last one that I'm going to talk about is the Repurposing Abandoned Oil and Gas Wells project, which is funded by Department of Energy. So our motivation here is to provide an alternate to conventional geothermal systems in low temperature areas like Illinois, and to eliminate the capital cost of geothermal systems, because if we're talking, so now we're switching gears from shallow systems to the deep systems, where we can generate electricity. So Illinois, especially Southern Illinois, is very rich in oil and gas wells, especially gas wells. And some of them are not being used at this point because they're matured enough, or they were just abandoned. And a geothermal well drilling is the most expensive thing in the geothermal system development for electricity. So here, the wells are already drilled, and we are trying to save money. And also, these wells are high risk to the environment. So there are a lot of lawsuits going on, especially in around Mohammed, to my knowledge, because of the methane contamination of the groundwater. By utilizing these wells, we are aiming to reduce these methane emissions as well. And our objective here with this project is to demonstrate the viability of this approach via full-scale field experiments. So this is a collaboration between ISGS, Prairie Corporation, and also Department of Civil and Environmental Engineering. The way to do it is simple. So you just need a heat source on the subsurface, on the surface. This can be anything. So this can be a solar power plant, and just to heat a water and then inject it through the wells, and then just heat up a formation which is initially at low temperatures, and then use this to pump it back up to send it to to push a turbine on a surface infrastructure to generate electricity. So these are the snapshots of the projects that we've been working on. And as a summary, the geothermal systems are environmental friendly. They help us reduce the fuel demand and decreasing CO2 emissions. And they require very low maintenance, and they can go for a long lifetime. They have a long lifetime. So they are space efficient, and they are also less vulnerable to the variations of the ambient conditions compared to wind and solar, because it's in the subsurface, and there is a great resource that coming from the core of the earth, and so less sensitive to energy price fluctuations as well. So I would like to just stop here. I hope you enjoy this very brief but detailed presentation. If you have any questions, you can reach me at tbaser@illinois.edu. Thank you.
Thank you, Dr. Baxter, for that great introduction to geothermal and some of the projects going on campus. Would remind you, if you've got questions that we can address now, to type them in the chat, and we'll ask those later on. And also remind you that we will be doing additional ones where we'll dig a little deeper into some of the campus projects. So that was just kind of a taste of an introduction of the things. So now I will turn this over to John Freitag, who is executive director of the Geothermal Alliance of Illinois, and it's a statewide association of the geothermal heat pump industry for our state. And he's, some things about John. He's got 30 years of experience in the utility industry, and then overlap that with experience in geothermal, and he has both geothermal heat pump and solar PV panels on his home in Springfield. So he's got that real world experience we like to add to this. And he's going to give us a good high level overview of the technology, heat pump technology, and where the industry is right now. So John, I will turn this over to you.
Thank you, Jay. I think I'm unmuted, but having a little technical difficulty on my end, getting my PowerPoint, so bear with me.
Okay, I ran through that a little quicker than,
Through that a little quicker than I had hoped, but bear with me a second. And hopefully, are you? And are you seeing my screen?
at this point, we are not, unfortunately.
Well,
I'm happy to share your slides if you want to prompt me for slides if you'd like. Or you can try to share again if you'd like.
Sometimes the joy of technology.
yes, I agree. So Nancy, do you have my slides handy?
Sure do. Yes, I do. Yep,
So if you,
I'll share.
if you would like to just share yours, I've got them pulled up, but they're not sharing off of my screen. So I've got about 20 slides, and if you want to just play them there, that would be fine.
Okay, let me know if you can see that properly.
I absolutely can. So that's a title slide. Go ahead, just scroll through them as. Keep going. So I will say, my name is John Freitag. I'm the Executive Director of the Geothermal Alliance of Illinois, and we're the statewide trade association for the geothermal heat pump industry in our state. And we've existed since 2008. A couple slides I think are going to be duplicates here, so we'll run through them. I will say that typical, what I call geothermal 101, or a good overview of residential and commercial geothermal heat pump technology, typically takes about an hour. I do a lot of these. We had 10 minutes for this, so this is really, really boiled down. But you can, if you want to get a Geothermal 101 good overview of geothermal heat pump technology, there are many presentations that have been taped for the Geothermal UC Group Buy program, and you can access those real easily. I also put my contact information in the chat, so you can just reach out to me by email, and that would be a good way. So we know that the Earth is a giant solar collector, and this is basically what makes geothermal heat pumps work. And go ahead, Nancy, and with geothermal, we just take advantage of that. You saw this slide earlier. What's key about this, if you think about this in common sense ways, you see that in central Illinois, really most of the state, we're right in the mid 50 degree range. I know in Springfield, my loop field runs almost always at 54 to 55 degrees. So depending if you're a little north or a little south, we're in the mid 50s. And what's important about this for geothermal heat pumps? Well, look at the far south, South Texas, South Florida. You see those really high groundwater temperatures. What are you trying to do? What are you trying to do in those regions, in those climates? You're trying to do air conditioning nearly all year round, very, very little heating load. So you're trying to inject heat into the ground, which is already much warmer than in central Illinois. Conversely, if you're in northern Minnesota, Canada, what are the groundwater temperatures there? You see, they're much cooler than in central Illinois, the low 40s. And what are you trying to do there? Virtually all the time, you're trying to take heat out of the ground using geothermal, and the groundwater temperatures are much cooler. So we're in the perfect sweet spot in central Illinois because we rotate back and forth between heating season and cooling season. And we've got a very great heat exchange temperature midpoint at 54 to 55 degrees, which just works perfectly. And so we toggle back and forth between heating and cooling season. And that's why geothermal is suited so well for Illinois, really all of the state, and really most of the Midwest. Go ahead, Nancy. So this is a very important slide in terms of the underground temperatures. So we know that the earth is a source of heat in the winter. Go ahead. And it's a place to reject heat in the summer. And when you're in air conditioning mode, we're actually taking heat and injecting it into the earth. Go ahead. And we use geothermal heat pump technology for this. Again, go ahead. So a lot of people think that geothermal technology is really new, and it really isn't. If you look at the nameplate here, the date on this Life magazine from 1948, October of 1948, go ahead. You'll see that there was an article in that issue of Life magazine on the fireless furnace, and this was really very primitive but earliest geothermal heat pump installation. And it was pretty crude, but it actually worked. And over the years, there have been many advances. Primarily, the early ones through the 70s and 80s and 90s were in outdoor piping, because these early systems used copper and steel piping, which they figured out didn't work in the ground. Today's piping is virtually indestructible and has a 50-year warranty, but for all intents and purposes will last in the ground forever. Go ahead, Nancy. So geothermal heat pumps are the most efficient and best heating cooling technology available today. That's the word from the US EPA, and they've basically stated this for the last 10 years. We know that it's the greenest heating and cooling technology by far. And we also know that geothermal and solar are a perfect match. Personally, I've had geothermal in my own home since 1999, so 22 years now. Before that, I worked in an office building that had its first geothermal system installed in 1985. So I've been around geothermal for a long time. I've had solar in my home, solar PV in my home in Springfield, almost 8 years now. So I can attest to the fact that solar and geothermal are a perfect match. I like to call them a match made in heaven. They work perfectly together. And in the presentations that we've done for geothermal, you see we get into a little bit more detail. So the reason that geothermal heat pumps work so well is that you're not burning fuel to make heat. You're really using electricity to pump water and blow air and take the energy that exists naturally in the ground. Remember, the earth is a giant solar collector, and you're basically using electricity to just move that energy. So again, you're taking heat out of the ground in the winter, bringing it into your home or your business, your office facility, whatever. And in the summer, you're injecting that heat back into the ground. And along the way, you're making free domestic hot water with your geothermal system. And that's why geothermal is so efficient, because you have no fuel to burn. You're just basically moving the heat. Go ahead, Nancy. So this graph shows the absolute cooling efficiency in EER. And you see the dark bar, that's today's geothermal systems, and you see the cooling efficiency, and it's measured in EER. Most of you are probably familiar with SEER. That's seasonal energy efficiency ratio. Geothermal knows no season because the groundwater temperatures are consistent. So we measure in EER. Go ahead. And in heating, we measure by COP, coefficient of performance. And this is where geothermal really shines. So you see conventional technology, gas furnaces, in the yellow and blue graph. And this is the laws of physics. And you see the ultra high 500% efficiency new geothermal units in the green bar. And this just demonstrates the high efficiency of geothermal heat pumps. Go ahead, Nancy. We don't have enough time to really get into the various types of geothermal systems. The previous presenter got into this a little bit, but I will say that probably 85% of the installations, the residential installations in our part of the world, are vertical closed loop systems. And this schematic shows a little bit of that. So we're going to focus on that. If you want to learn more about the various loop systems, open and closed, horizontal, vertical, they're all in those geothermal 101s, or I'd be glad to help anybody with any of that information. But because we're real short of time today, we're going to focus on the vertical loop field. Go ahead, Nancy. So this is what a borehole looks like. So this is the fuel tank, if you would, for the geothermal heat pump. This is the borehole that goes into the ground, and typical depths for residential systems are 150 to 300 feet. 150 to 200 foot depths are very, very common for geothermal systems in our part of the world. And I believe they said that the new facility had 40 300 footers on campus. So that would not be uncommon. So a drill rig that looks very similar to a well drilling rig drills this borehole, and immediately after the borehole is dug, the piping is set into the ground. Next slide. And then immediately after that, that borehole is backfilled with bentonite grout. And so this is actually what it looks like. That sliver would look like. Go ahead, Nancy. So again, we don't have enough time to get into great detail, but in summary, the newest geothermal systems are all 500%, give or take, in that ballpark, 500% efficient. And they do that really through really efficient electronic controls, and they use up to 30% less energy than many of the systems that were installed as recently as 4 to 5 years ago. They tend to be more in the 400% efficiency range. The new equipment, or geothermal equipment in general, provides really even temperatures for the ultimate in comfort. It's perfect for zone systems. Provides the ultimate in flexibility with some of the new systems provide on-demand hot water, 100% of the on-demand hot water. I know my system in my own home provides 100% of my hot water when we're in cooling mode, and approximately 50% of my hot water when I'm in heating mode in the winter. But the new systems can provide 100% all the time, whether you're at heating or cooling. It can just be running just to provide hot water. And again, they can be used in conjunction with wireless controls. I know I operate my system with my iPhone. Last night I was coming home from Wisconsin, and I got between Bloomington and Springfield and adjusted the temperature in my home so that my house was nice and cool when we got here. So that worked really well. Again, go ahead, Nancy. We're nearly done with my part. We have some great opportunities for schools and municipal buildings in Illinois. Most people don't realize the great number of schools, middle schools, elementary schools, high schools in Illinois that already have geothermal heat pump systems. Again, everything is either the mechanical equipment is in a mechanical room, and everything is underground. So it's out of sight and out of mind, unlike a lot of other renewable energy technologies. So you really don't see it. But in Central Illinois, Northern Illinois, there are many, many school districts that have been using geothermal for a long time now because they are so efficient in those buildings, and operating costs are typically half or less than conventional systems. Maintenance is almost always much easier and much cheaper. There really isn't a whole lot of maintenance to do. And again, equipment tends to last a long time because there's nothing outside on roofs or on the outside of buildings that is exposed to the elements of weather. So equipment lasts forever, and the loop field that's underground lasts virtually forever. Again, Nancy. But why are geothermal heat pumps still a niche product in the United States? Well, they cost more to put in, primarily because you have to put that loop field in the ground. So they cost more upfront. The technology really isn't all that well known, especially in areas northern Illinois. The Chicagoland region does not have a big imprint of geothermal. Over the years, we find that some in the engineering community have given geothermal a bad rap. They don't design geothermal systems, so they don't realize how good they work. And then many of you have heard stories about heat pumps in the 70s and 80s and even 90s, air source heat pumps that probably worked not as well as they should have. And air source heat pumps are better today than they were back in that era. And both technologies are heat pumps, but they're different in that air source heat pumps extract heat out of the air and they inject heat into the air in the summer. And geothermal uses the constant temperatures underground. And we know that temperatures fluctuate greatly. It's pretty hot and humid out today. So it's a little bit hard to inject heat into that hot, humid air. And underground, it's still mid-50s. Go ahead, Nancy. So what can a community do to promote geothermal technology? Well, you can incent and promote with local developers. You can promote and provide tax incentives. You can encourage and promote community loop ownership. Community loop ownership is not a concept that has really taken off well in Illinois, but has become real popular in states like Texas. It's taken off. And when that happens in Illinois, when we see community loops, that will really drive geothermal installations because it provides an economy of scale. And what a community loop is can think of this as a giant loop field, and then different facilities, homes, for instance, can take a sip off of that larger community loop. So you get a real economy of scale that can happen there. Again, ownership of the community loop by a developer or the community, that would be a great promotion. Communities that install geothermal in public facilities like the university, like City Hall, schools, recreation buildings, those are great examples of facilities that can take advantage of the efficiencies of geothermal and promote to the public. And then lastly, we want to talk a little bit about group buy promotional programs. And many of you realize that we had a program like this in Urbana-Champaign the last year. We just got done with the first year of the program. Nancy, go ahead. And we had the geothermal UC program. And again, I think that I saw Andy put something in the notes with the link to the geothermal UC. And if you're interested in seeing a more in-depth, primarily a residential geothermal overview, I call them Geothermal 101, you'll see that there are many of these presentations that are taped and available there. And I think that's all I've got. Nancy, was that the last slide? I think. There's my contact information. So thanks for being part of this today. We tried to boil this down to something that would move along really quickly. And we skipped over a lot of detail, but I would be always glad to help anyone with more information. Please reach out to me. Or again, if you want to see a good overview, just go to the Geothermal UC site and check out the presentations there. We call them the power hours. Jay, back to you.
Thank you, John. Thanks for the overview of kind of what's going on out in the industry. And this is probably something for everyone we're going to come back to at some point and dig a little deeper into this. We intended this to be a good overview of what's going on. So our last presenter today is Yu-Feng Forrest Lin, Dr. Yu-Feng Forrest Lin, and he's the director of the Illinois Water Resource Center, a principal in research hydrologist with Prairie Research Institute, a clinical professor in the Department of Civil and Environmental Engineering, and research professor in the Department of Natural Resources and Environmental Sciences, all at the U of I in Champaign, Urbana. So I didn't know which one of them to cut out. So he's involved in a lot of different things. Received his PhD in geological engineering from the University of Wisconsin-Madison. And he's going to highlight some of the things that are going on significant to groundwater and groundwater infrastructure pieces of that. So I will turn it over to you, Dr. Lin.
Thank you very much, Jay. And can you hear me and my audio video okay?
You look good. Look and sound good.
I'm sorry?
Yeah, the things are looking sound good. So
Okay. So well, first, thank you for inviting me, and then really great to see so many colleagues and potential friends interested on this technology. And I really want to thank Jay and Nancy to host this event. And I'm grateful to be able to elaborate a little bit more on what Professor Baser and also President Freitag presented earlier with all of the insights. So today my presentation is basically to show you a little bit more scientific evidence on all the benefit and then the advance on what Professor Baser and President Freitag mentioned earlier. So this talk will be based on another presentation I gave about a month ago, invited by European Union, their Horizon 2020 program. And so one of my colleagues from USGS and myself representing US and to give this talk to the whole European Union community on the geothermal energy. And so before I start, and I just want to give a quick background on why are we doing this? And then this kind of elaborate figure that Professor Baser used earlier from a DOE document. So just double check, Jay, you can see my cursor, right? Okay.
yes,
Okay.
too small, we can't see it.
Good. So this a tiny figure here is from one of the DOE report and tell us 80% of our thermal energy usage is below 150 degrees Celsius. And then that means the majority of our thermal energy need is low temperature. And then within that total 80%, almost 40% of that thermal energy need is only between 40 degrees Celsius and 60 degrees Celsius. Then go back to Professor Baser showed earlier on the bottom diagram here. The DOE identified in the geothermal usage, there are 11 applications. And in those 11 applications, 8 of them are the low temperature and not for electricity generation. On those 8, 7 of those 8 is applicable in Illinois. So just some number to give everybody an image about why we are talking about this here in Midwest, in Illinois, and why this is good for your city, for your farm, for your house, or even for your backyard. So I'm a hydrogeologist. How did I start getting all of this? Because I had I got involved with one of the NSF project, National Science Foundation project. It's called Intensively Managed Landscape Critical Zone Observatory. And then in this project, we try to understand critical zone, which is beneath canopy and above groundwater system. And then as NSF defined, about more than 95% of the activity, biological activity is in this zone here. And during our study, I was in charge to try to understand how the climate change and also human activity will impact on the subsurface temperature regime on that. And the impact of that will kind of show us a picture about how temperature propagate because of climate change, and then how the agriculture activity will have interaction with subsurface temperature. And also when we install a well, put a plastic pipe in there, what's the interference of that? So we had a site at Rantoul, Illinois, and it just happened when we installed that day, Google Earth took a picture from their satellite. And then our truck, our installation truck, it was all there. And then in this project, we installed 2 wells. One is a borehole 100 meter, and we put fiber optics down there to measure temperature. The other one just about 2 meters away, which is about 6 feet, 5 to 6 feet away. We have another well, which is 14 meter, and we screened and down to the glass aquifer. And the borehole is all the way to the Mahama aquifer. And then during this study, in our deep borehole, which is 100 meters, go all the way to Mahama aquifers. In the shallow part, in the top 16 meters, the data we collect over a year, monthly, it corresponds to the conventional study very well. The temperature turbulate near the surface and almost become constant when it reach 16, 15 meter depths. And this diagram, it shows very similar on what Professor Baser shows in her presentation. But however, the scale of the temperature resolution is about 1 degree Celsius. Our instrument using fiber optics can measure all the way down to 0.01 degree resolution. When we use the high resolution in this scale, you see even just 0.2 degree resolution, the temperature is not constant. If you use like a magnified lens to look at the temperature, and then very interesting, the temperature gradient, temperature change just follow along all of the geological formation, especially the slope change dramatically when it reaches Mahama aquifer. This gives you as an indication on how much significance groundwater related to the thermal regime in the subsurface. And that's how we all start all of this, about how important is groundwater to subsurface and even for the geothermal energy design and study. Then another case, that 40 meter well also shows when aside when we have well, when we don't have that well with the plastic, the change of the blue curve, which means there's a well there. The orange has no well in there. When we sit down at the 5 meter depths, 4 meter depths, 3 meter depths, you start seeing the curve is doing different of the perturbation based on the surface temperature, and which means that plastic pipe does have the impact on the subsurface temperature profiling, or we say the thermal transfer of that. One well might not be a big difference, but what if our infrastructure in the subsurface, for example, in the city, you have the water supply system, or you have sewage pipe, and you have steam tunnel, or you have even subway system? How is that going to change of all the subsurface temperature profiling? And then also in our like a rural area, when we have, let's say, remediation well field, when you have 30, 20 wells, how is that going to change the whole regime of it? So this the initial study shows us using rule of thumb, try to understand the subsurface temperature. It's not really this way, it is this way. We need to have much more detailed study, and especially when President Freitag talked about installation cost for geothermal is high. Once we understand the subsurface better, I think we will have a very good chance to reduce our initial installation cost. So that's why at the University of Illinois, we established a geothermal research station on our campus. And then we mimic on the vertical loop, as John mentioned earlier, but we also put an instrument to measure how this loop will behave in very, very detailed spatial resolution and temperature resolution. So inside the loop, when we do the simulation, very similar to what actual heat pump works. And the simulation is not computer simulation. This is the real data. We inject water and they mimic how the ground source heat pump works. Inside the loop, this is where the water coming, and then this is water come out because it's a U loop. So the bottom of the U loop is in the middle of it. So we can see, just take half of that U loop. Inside the loop, the temperature, yes, is linear, but outside of loop, the temperature change with time, it corresponds to geological formation perfectly. And even when the loop cooling down, we stop the water circulation. The cool down curve inside the loop, outside the loop, all corresponds to the geological formation perfectly, especially when you hit aquifer system on that. And the response is even more obvious than dry formation of it. So we use this kind of such study to help our own geothermal system installation. So also, as Professor Besser mentioned earlier, on this campus project we had just finished, the original design was 60 loops. And because our study in a really fine resolution, and then to improve the design process, we cut down 60 loops all the way to 40 loops. What does that mean? That means we can pinpoint efficiency for the exchange in the subsurface much better than just use rule of thumb. And which also means the financial benefit, the original design for the payback is 40 years. Now we only need 28 years to have the payback operation to cover this cost. And then during our study, we also found this subsurface temperature regime. It was not quite like what we had earlier. When we hit about 10 meter depths, the temperature just certainly hiked. And then we was wondering what's going on there. This is very different than what we study or what we expect. And then we realized, oh, 10-meter depth is where the university steam system is. And that steam system really shows a big temperature hike, no matter what season we have in there. So on all of those data, what I want to show you in very briefly sense is how important we need to understand subsurface on the property of the geological formation and also the groundwater system. What we understand the flow, the content, and then also don't forget about our artificial infrastructure, which could be an anomaly for our subsurface temperature changing, but also it could be a potential for us to harvest some of those heat. And here, that's why I don't want to say conclusion. It's a summary to show you those are scientific evidence to show you we are doing geothermal exchange. The equipment for the heat exchanger has been improved so much thanks to our mechanical engineers. But again, we are using subsurface to be the exchange media for our benefit on the heating or cooling part. And subsurface is the key for us to improve this technology and cut down our cost. And that's why myself and a lot of our colleagues are working together very hard and try to improve this great technology. Look at what John shows, 500 times much better. This is even more improvement just from geothermal to the conventional way. It's even more than LED compared to the conventional light bulb on this. And this LED of the energy is not done yet. And we are doing much more study, try to make it better. And so we are really in the leading age for such technology improvement and scientific study. So even now we are working with scientists around the world from Europe, from Asia, and then we are publishing all of the advanced paper in the top journal of our field on this. So this is a quick update for everybody about the scientific evidence and then the current progress and our future plan of this. So I'm happy to answer any question along with my colleagues, John and Tugce, and after my presentation. And I think this is the last slide of my presentation. Thank you very much for your attention.
Thank you, Dr. Lin. Thank you to all of our presenters. And at this point, we do have a few questions. There was one kind of a detailed question about cost that that John actually, James Ryan Hamilton asked, and John responded back in the chat about it. John, do you want to make any more comments about that relative to budgeting? How much you would budget if you're replacing a system?
Sure. So as I told Jay in the chat as we were going, I hate to throw out generalities because different parts of the state have different costs. Drilling and loop installation tends to cost more in northern Illinois than it does in central Illinois. Drilling can be a little tougher there. Drilling in central Illinois is pretty cookie cutter in most of our areas. We have pretty simple clay soils that are easy to drill through. I know in Springfield, it's very, very cookie cutter. And when you run into different types of soils, it can be a little more complicated. So there's less infrastructure for our industry in northern Illinois. So that means there's a little less competition, frankly. And drilling is just different there. So loop installation costs more. But in general, and this is a wide thumbnail, in general, a very wide thumbnail. In general, you would find that residential geothermal installation costs tend to run in the vicinity from $4,000 to $6,000 per ton of installed capacity. And Jay gave me the hypothetical, I think it was a 2,500 or 2,700 square foot home, Jay. Maybe that was your house, I don't know.
It was actually from one of the client, from somebody, it was an individual asked that question.
Okay,
2,700 square feet.
So let me just use my own home in Springfield, Illinois as an example. So I have a 4-ton system. My house is 2,900 square feet. It was built in 1961. It's about as good as a home from that vintage that hasn't been completely, and I mean completely, ripped apart and redone. So it's got old fiberglass insulation, lots of windows, but it's pretty good for that vintage. I have a 4-ton system. My geothermal system runs like gangbusters perfectly. And it would cost in the vicinity to put in brand new, it would cost in the vicinity of the low 20s for a 4-ton system. That same system in the Chicagoland region would be more money than that, frankly. permitting, everything's different in different parts of the state. So that's why I hesitate to get into prices, but that kind of gives you a general idea, if you would.
Gives us the kind of the range that people are looking in, and I think that's helpful to everyone. Very quick question for you is how do you find out how efficient your an older geothermal system is? If you've got a geothermal system, is there a quick way to check the efficiency on it?
Sure, because you can look at the nameplate on any system and pull off the information on that. So just as a general ballpark, I'd say the system that I put in at an old water furnace system that was installed in my home in 1999, that one was about probably 325% efficient. That was kind of where we were back in the 90s. And the system that's in my home now has been in for, I changed out my mechanical system, I guess, about 3 years ago. And I'm probably about 400 to 450% efficient. And the new systems with the really high-tech electronic controls are in the 500% range. So pretty darn good. But yeah, you can get exact numbers on all of that for sure.
Okay. That's what I thought, like all the rest of them, they've got to have a nameplate on them.
Mhm.
So this question's for the other part of the group here. Do the university dorms use geothermal heating and cooling? And if not, what are the plans to implement this? So
Yes, I think Andy already answered that question by typing in the chat. And since we got a lot of questions here, maybe we can go to the next one.
okay.
Yeah.
Can one system be set up for multiple houses, multiple buildings, two side-by-side buildings, say a greenhouse and a church? And I think Andy kind of answered that question. And I guess that maybe Dr. Baser, do you want to kind of touch on that relative to the buildings on campus, otherwise?
So can you repeat your question? Sorry.
Well, there was a question about systems being set up for more than one. For two buildings.
Oh, okay, yeah. So so this can be definitely done. So there is like a very significant push to actually upscale the single home ground source heat pumps. So they work pretty well, but we know that we can save a lot of money when we upscale it to the community scale. But one thing that I don't know why, but the development here in the country, for some reason, it's kind of like it's not moving towards the community scale development. So we are seeing examples, especially in Canada, in Denmark, Sweden. So this has been just like moving to the, so when we first develop the systems, they think large scales, and then it's been proven by different research approaches and different research methodology that these systems work better, and also it's less costly when we do the community scale. So there are, again, we acknowledge this development in the world, and we are trying to adapt, but I'm not really sure how we will be moving forward. But I'm hoping that with this new infrastructure bill, we will have a lot of opportunity to do it at the larger scales, at the community scales, because when we talk about community scale, so that means integration of buildings, residential buildings or commercial buildings, and roads, sometimes bridges, bridge foundations, and sometimes even tunnels. So but I'm sure that there will be more development in the near future, and we are hoping that there will be.
Okay.
So Jay, let me take a quick whack at that and try to simplify that question. So the real question was, can you have a one loop field to serve multiple buildings? I think the actual question was, can two buildings two facilities be served off of one
Right.
loop field? That's the specific question. And sure, you can do that. That can work just fine. And it might be an extremely efficient installation, because you might have one of the facilities that, let's say it's filled with electronic equipment, and they might be in cooling mode virtually all the time. And the other facility might have a much greater heat requirement. So the two would use the loop field essentially to move energy from one to the other. That, so that can be a very, very efficient installation. But the key thing to remember is that the start of any geothermal project, and it doesn't matter if it's a 2,000 square foot home or it's a 40,000 square foot facility on a university campus or anything in between, you have to start with the load. You have to know what the heating, cooling requirements are. If you don't have that, you can't do geothermal efficiently and effectively. You can't make it work. You need to know what the load is. And so in the case that you threw out, you'd have the load of those two facilities, and you would design the loop field accordingly, which is what Yu-Feng was talking about with their test bore. And they designed that loop field off of the load and the geological characteristics, getting that information from their test bore, and they've got an extremely efficient and effective system there, obviously. So that is the way to do it. Does that help?
That helps.
Okay.
I think I guess to the target. I think kind of this means, how long would a residential system last? Do the pipes wear out or leak, or what some of that concerns we would have in it? And I know this is something we're probably going to look at a little bit in some of the future ones as well.
I can help here. I was just getting up. This is actually, that's a piece of piping. That's actually a 5-ton header for a residential system. That's how the piping's connected before it comes into the home. But if you can see this, that's actually what the pipe looks like. Sorry. And so this is essentially what my loop field is out in my front yard, 20 or 30 feet from me. This is a 3-ton loop field. And if you think of this as being 175 feet in depth, that's what my loop field is. I have 3 loops just like this in my front yard that are 175 feet in depth. And then that is connected via here with 2 pipes that run into my house. Pretty simple. Now, the piping is guaranteed in the ground. This is HDPE pipe for 50 years. I say it will last forever. Frankly, the enemy of underground of a loop field, whether horizontal or vertical, there's 2 enemies of the loop field. Number 1 is a backhoe. You go digging and you cut into a loop field with a backhoe, you will damage it. That makes for a very bad day. It doesn't happen very often, but it could happen. That's number 1. Number 2, and this is hypothetical, I think the other big enemy is an earthquake. If we ever have the absolutely terrible, massive earthquake in southern Illinois, central Illinois, that could damage loop fields, but I think we've probably got bigger fish to fry if we get to that point, because the buildings that are served by that vertical loop field have probably been destroyed.
Right.
Hopefully that helps.
If I may elaborate a little bit what John says here, if you see John's pipe under his arm right now in the bottom that you loop, regulation require that to be fused. It's not like your water pipe, regular water pipe, use glue to glue it down. So it's fused, a very special equipment fused, and just like the original pipe. And that's why it won't leak. It's not like plumbers using glue and then turn purple and kind of glue in here. But on the surface part, that might have a leakage, because on the surface connection, it doesn't require to be fused. But the only, usually what residential and scientists like me, what we worry about is the leakage in the deep subsurface system on that, and which we learn is that the fusing process is pretty restricted on that. So thank you.
Once in a while, I'll hear about a leaking loop field. It's pretty darn uncommon, to be honest. Once in a while, you'll hear about a leaking loop field, an older one that had fusion that failed underground. Gosh, it just doesn't happen that often. And there are such good products for fixing that now that you don't always have to dig it up and replace it. And to be honest, I haven't heard of one of those for so long. I'm sure they happen. It's pretty uncommon, very uncommon, to be honest.
Right. At this point, there was a question about the break even, and I think you answered that. But
I can
taking
take
it one step
I can take
further,
a short whack at that if you want, in 1 minute or less.
how much would break even and the payback period, especially if we're looking at energy prices change? And I think I know what the answer is that pretty quickly.
So here's the quick way to consider costs. And we're talking residential systems. So in the geothermal world, there's an old saying, double and half. And geothermal might cost as much as double conventional systems, and the operating costs are half. And I find they're usually less than half. But that gets you in the ballpark, at least gives you something to chew on and think about, okay? So let's say a typical residential home, the one we were talking about before, that system, that geothermal system might cost, let's just say $25,000 to install. And by comparison, if you had to replace the heating and cooling system in that home, and you were going to put in a conventional system, a gas furnace, and a central air conditioner, that system would likely cost roughly half of that, give or take. Let's just say $13,000. So the difference is $12,000, right? Well, you're going to qualify for a tax credit that's currently 26%, will very likely return to 30% tax credit, which is the same tax credit that an individual would get for a solar system or a wind system. So you deduct the cost of that tax credit. So it's not a tax deduction, it's a tax credit. And help me with the math here, Jay. We've got smart people here. What's 26% of $25,000? It's roughly $6,000, give or take. Are we in the ballpark here? So you knock that off of that price. Now you see the incremental difference is more like $5,000 or $6,000. And in many areas, you have incentive programs from utilities. So for instance, ComEd in the Chicagoland region has $1,000 a ton rebate. So for that same installation of 5 tons, that homeowner would receive a $5,000 rebate from ComEd. So you knock that off the cost. Do you see how you're getting to the point that geothermal doesn't cost much more from conventional systems? And then in Champaign, Urbana, we ran the geothermal UC program last year, and we had extremely competitive prices, very, very good prices for geothermal installations there. So you start putting all these things together, and the truth is geothermal doesn't cost a lot more compared to conventional systems, and they operate at half the cost and have double the efficiency or better.
Right. So there may be a few more questions. I'm not sure too much out there. One of the things I know that Nancy has triggered the knowledge, or is triggering the knowledge gain piece. And so if you would just click right there on to answer the questions right there on the screen for us. And Nancy, can I put up the other slides in behind that?
Sounds great.
Couple of pieces here you should be seeing now is we do have 2 more of these in this series that we're going to be doing. One is geothermal projects, and we'll be looking at geothermal energy campus case studies. So digging a little bit deeper into some of the projects that were highlighted earlier in this by Dr. Lynn and Dr. Bashir. And then some other projects are on campus. And then that one is August 12th or August 10th. And then on the 12th, we're going to dig a little bit more into the community cases and a little bit of what we were just answering, the things about similar to the Champaign Urbana-Champaign project that went on, and also some of the home projects that the individual home projects that are out there, in looking more of a community scale piece of this and how to get those projects started. So if you're interested in that, please consider joining us. That's the first one's on the 10th and the second one's on the 12th. Both of them will be at noon, just like this was. So no, we went a little bit over this time. Appreciate everybody bearing with us. We had a lot of material to try to cover in a pretty short time frame here. And I guess that I lost track of in doing that, I lost chat for a moment. Were there any additional, did anybody catch any additional questions in there?
Jay, someone asked about can a system be, the price of the system be put on someone's home, I guess the mortgage. And to my knowledge, I don't think there's a residential, what they call a PACE program yet for Illinois, but I think there's a commercial program, so you can actually put the price of your geothermal system on your property assessment, and then you can pay that off over so many years on your mortgage.
Right. Right. But you know, the other answer to that one is it is on the home side, it is your heating and cooling system. And so in some ways it can be integrated in there. Now, as you say, the being able to pay it down or adding to it all depends on how you do the paperwork on it. But when you go to sell that home, definitely it's going to be there. And if you buy a home with the option or the statement that, hey, the system needs to be replaced, that becomes a negotiation piece with your banking, your lender at that point.
Yeah.
And I guess I look at that one because I had to go through that one when I purchased my house. So with that, Nancy, do we have anything else that we need to do?
No, I just want to thank everyone for their time today. We are well over the 1 o'clock hour, but no problem. I think it was a great dynamic session. I just really want to thank everyone for their time and happy to do this outreach and hope we see you at the next sessions.
Thank you very much. And with that, I will say thanks to our presenters and draw this to a close.